we basically characterize the Nyquist stability criterion, right? We find out that as long as we know the information of the open loop system, then we should be, well, specifically, we know the Nyquist plot and the poles information of the open loop system G of S, and then we're gonna be able to predict if this closed loop system is gonna be stable or not based on that information, right? So that's what the Nyquist stability criterion tells. Okay. Now, if H of S is not equal to 1, then your open loop system, you know, the open loop system is the loop transfer function, right? From here to here, right? So exactly, if H of S is not equal to 1, then apparently open loop system includes H of S. So the evaluation becomes GH, not G. Okay. So if H is not equal to 1, you cannot drop the H. You need to include H in the evaluation. You need to obtain but the principle is the same. You still get the poles of this transfer function. I mean, counting how many poles in the right half plane, and then you need to draw the Nyquist plot of GH, not G, right? So it's not a big deal, okay? But like what I said, normally we can use the scaling method approach to make the H of S to make the feedback system is a unity feedback. The loop transfer functions stability is not important. Okay, I mean, in terms of the stability requirement, it is the always, like what I said, all the performance requirements are posed for the closed loop system. Okay, the open loop system, it's whatever open loop system, you got it. It's not up to you. Okay, but you could have a good, you could have a bad, open loop system. Okay, so what is more important is that after you apply the controller and obtain this through this feedback structure, so what is going to be the behavior of this closed loop system, that matters. Okay, that matters. So you should be careful about that. Okay, okay, yeah, okay. So so what do you mean? What do you mean? I don't understand your question. Which one is not a open loop system? Because we include the feedback. You include feedback. Well, this is in the feedback channel, right? The H of S is in the feedback channel. But when we say feedback system, we mean that you close the loop here. You see the open loop. Why we call this one open loop? Because we break the loop here. Okay. So if you break the loop, then this guy here, the signal here becomes the output signal, right? So your open loop is going to go through a G and through H to reach this point, but not feedback to the summing junction. If you feedback the signal to the summing junction, you form a closed loop, and that's the closed loop system matters. You see what I mean? So that's the difference. Okay, you know what? You need to go back to check the control 1's notes and to recall those definitions. Okay, this open loop or closed loop issues we talk about a lot. We defined it clearly in the control 1, so you need to go back to check those notes. Okay, I can't repeat too much here. Okay, so I've just used the concept, the open loop, the closed loop. Okay, all right. So now, yeah. So I also mentioned that there is a very important special case. Is that when the open loop system G of S, it's stable. Okay. Well, here you can understand here we imply that the H of S is actually equal to 1 here. Okay. Right. So we only need to check G. If H of S is not equal to 1, check GH. So if this open loop system G of S is stable, that's actually a special case, but that is a very important special case. Okay, So in this case, we know that the P is not equal to 0. P is straightforward equal to 0 because there's no right half plane open loop poles, right? So you can see that the stability, the N in this case is going to be equal to Z. Okay? So the stability criterion then can be simplified to what? To just like you check if the G of S's Nyquist plot is gonna encircle the -1, 0 point or not on the G of S way, right? Okay, so we talk about that. So this in this case is straightforward. You just need to see if there's any encirclement. If there's no encirclement, closed loop system is stable. If the encirclement happens, yeah, the closed loop system is not stable. Okay, that is a very important, like what I said. Most of the cases that you do have a stable plane model, okay, which means that most of the physical system, your open loop system is stable. But I did not exclude the case that the open loop system is not stable. We do have the physical system, the open loop system, it's not stable. Okay, so just be careful about that. And also, this one, this simplified Nyquist stability criterion actually can give us introduce another very important, concept, which is the stability margin. Okay, because you know what? Because you see, right now we can simply just use if the Nyquist plot is gonna encircle this -1, 0 point or not. So then one good question is that if we try to modify the G of S's Nyquist plot, well, we can only have two ways to modify it to affect the Nyquist plot, right? Magnitude and the phase. Okay, so if you look at this figure here, okay, if you look at this figure here, this is the Nyquist plot of the G of S. So you want to modify the plot, you have two ways, either magnitude or the phase, all same time. You change the magnitude and the phase same time. So you can see that when you change the magnitude, then the magnitude is going to be expand or shrink. Okay, either expand or shrink. It depends on, for example, if you apply the kg to it, and depends on the k is larger than 1 or less than 1, then you're going to expand or shrink the magnitude. So I talk about this, right? So if k is larger than 1, let's say if you apply the k, because the k is a pure gain, it is purely a gain, so it does not affect the G of S's Nyquist process of phase. Okay, it does not affect the phase, right? So in this case, it will expand the plot radially. Every direction, it's going to be expanded at the same times or shrink same time. Depends on the value of the k. So if k is larger than 1, then you basically will push this point to the left, right? If k is less than 1, then you are pushing this point to the right. Well, this is because we are evaluating the plot along this direction. Okay, right? I mean, each direction, it's going to be expanded the same times, but my major concern is along this direction. This is the -180-degree direction. -180-degree direction. Okay, right? So this direction is important. Why is important? Because if you keep increase the k and keep pushing this point, and this point is going to be kept, pushing to the left and the left and the left, well, you can see that there will be a k value such that this crossing point is going to be pushed to the -1, 0 point. Okay, so from this plot, you can see it very clearly. If you continue to increase k, then what? Then this point, this crossing point, is going to be pushed beyond the -1 point. Okay, if the crossing happens here, and you're gonna have a plot like this, and if you finish the whole plot, okay, if you finish the whole plot, you're gonna see something like this. Okay, see, encirclement around the -1, 0 point will happen. Well, because we assume the g of s is stable, right? Okay, so in this case, if the encirclement happens, you don't need to say anything else. The closed loop system will not be stable. So you can see that actually the crossing happens at the -1, 0 point. It's the critical point. Okay, they separate the unstable closed loop system and the stable closed loop system. Okay, so because of that, we define this this distance as a gain margin, because this is the how much that you can increase for the k, right? How much you can increase from this point. Okay, starting from this point, how much you can increase the k. So we call it the gain margin. Okay. Now of course we measure, because this is magnitude. So we normally measure it in dB, in 20 log. So that is why we have the following definition here. Okay, for the gain margin. For the gain margin. Okay. See, the gain margin, it is that you need to identify the, well, you see, let's look at this definition here, okay? And also, this is also the procedure to calculate this gain margin, okay? See, we need to identify, the most important is that we need to identify the gain margin crossing over point, like what I said. And this is the minus 180 degree direction, okay? This is a minus 180 degree direction, okay? Okay, and so you basically find out this crossing point, okay? And this crossing point, you know that this is the Nyquist plot. We already talked about it. The Nyquist plot, it's a parameterized plot, and parameterized by what? By the frequency. So corresponding to this crossing point, there will be a frequency, and that is this frequency, we call it omega GM. This is going to be the gain margin crossover, frequency. And actually, this is the frequency at which the phase is equal to the minus 180 degree, right? Okay, right? So this frequency, it's called a gain margin frequency. So we need to identify not only this crossing point, but also this frequency. Now, once we identify this point, then we need to do the calculation. So how am I going to calculate this crossing point? Yeah, you see, we can actually set up the imaginary part of the g of j omega equal to 0. Why? Because this is on the horizontal real axis, right? So the imaginary part at this point, imaginary part of the g of j omega must be equal to 0. So we use this condition, we can calculate the value, find the value of the omega g sub gm, okay? The gain margin crossover frequency, okay? So this frequency will make the imaginary part equal to 0, okay? Well, if you know the expression of g of j omega, later on we're going to show you an example, okay? So if you know the expression of g of j omega, well, you can easily find out its imaginary part, okay? Well, remember, you see, in the example before, we had this case. Remember, see, like oh, where's my calculation? Yeah, my calculation here, you see, if I have a transfer function like that, I can easily find out its imaginary part is this, okay? So you see, for example, for this one, you see, you want to calculate the crossover, and then you make this one equal to 0, okay? You make this one equal to 0. So you're going to find out the crossover frequency is what? Omega equal to 0, or omega equal to infinity, right? 2 omega corresponds to the imaginary part equal to 0. Omega equal to 0 and omega equal to infinity. Why is omega equal to 0? It's here. You see, the first crossover is here. And the second one is what? Infinity. Okay? Actually, you know what? This guy has a gain margin infinity. Okay? Because you see, the closing crossing point is at the origin. Okay? And the -1 is here. See, this is the 0. The 0, you see, 20 log, you know, 0 is what? 1 over 0 is infinity. Okay? So based on the gain margin definition, this guy actually has a infinity gain margin. In other words, you know what? If you use this transfer function to construct a feedback system like this, okay? And here it's s plus 2, and you put a k here, okay? Now you can test it. It doesn't matter as long as k is larger than 0, okay? You keep increasing k, and this closed loop system is always stable, okay? It's always stable. As long as the k is positive, the closed loop system is always stable. So this means that you can increase k to infinity. So that's why this the gain margin for this system is what? It's infinity, okay? It's infinite, right? So this is just a simple example. We're gonna see a more complicated example later, okay? But I just want to say that as long as you have the expression of a g of j omega, its imaginary part and a real part can be easily found out, okay? Okay, so now let us continue. So yeah, so once you find out this gain margin crossover point frequency, and then what? Then you can calculate its real part. Okay, you can substitute it into the real part. Okay, you only use the imaginary part to find the omega gm. So then second step is that you substitute this value into the real part. Okay, now into the real part, you could have find multiple crossover points. Okay, multiple crossover point could be happen for the horizontal real axis. Just like that example 1 over s plus 2, we found 1. We found 2 actually, right? We found 2. One happens at omega equal to 0. The other happens at omega equal to infinity, right? So one is at 0.5. The other one is at the origin, okay, the crossover. So you're gonna have a multiple crossover point with the real axis, right? But when we calculate the gain margin, it closes to the crossover point that counts. Closes. So, but only the one closest to the -1, 0 point counts. Okay? Okay? You know, the point is that if you cannot make the closest point to cross the -1 point, -1, 0 point, how can you make the crossover at the right-hand side to be crossed at -1, 0 point, right? It is not possible. So that's why you only need to identify the one that is closest to the -1, 0 point. If you increase the k, it is definitely that point, that crossing point closest to the -1, 0 point. It's gonna be crossed at first. Okay, it's like this one. See, like this one. You see, this one actually, you can in this figure. You know how many crossing point with the real axis? You have one here. You have one here. You have 2 here. Don't just think that it's 2, okay? Because you see, I did not complete the plot here, right? I did not complete the plot here. This plot might have the shape here. So you might have another crossing happens here. Okay, right? Okay, so this plot might have 3 crossing points with the real axis. But this 2, I don't count. Okay, I'm only concerned about the one that is closer to the -1, 0 point. Okay, like what I've just explained. If you increase the k, okay, kg, and you increase the k, and it is definitely this point first across the -1, 0 point. Okay, okay, this 2 is gonna follow up. Okay, so but we know that in order to predict closed-loop stability, as long as the encirclement happens, it is done. So that is why you only need to evaluate the closest point, right? Okay, so that is what I said here. Okay, you might have multiple crossover points, but only the one closest to the -1, 0 point counts for a gain margin calculation purpose. Okay, now the third step is that now you can calculate the gain margin based on this calculation, based on this definition. It is going to be -20 log double bar, the absolute value of the real part of the g of j omega gn. Okay, like what I said. Okay, calculate this is the closest point, absolute value, magnitude, closest point, right? So it's here. Okay, it's here. Okay, so why it's why it's a -20 log? Why it is -20 log double bar real of g of j omega gm? Well, you know what? This one actually is equal to 20 log 1 minus 20 log double bar real, right? Okay, you see, like what I said, I've just said that I want to measure this distance as the gain margin, but in dB, in 20 log. So this point is what? Is 1. Absolute value is 1. So that's why you have 20 log 1 here. And then minus, you see, minus 20 log double bar real, this point. Okay? So you measure this 2 points distance in dB, and this is it. So, but this one give you the 0. So that is why this is the formula to calculate your gain margin. Okay? 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 So this is the gain margin calculation. Very easy, right? Okay, so you just need to find the expression, follow this step, you'll find the gain margin. Okay? And apparently, this way the gain margin is also measured in dB. Okay, so that's why in practice we normally talk about, oh, I have a 3 dB, I have a 6 dB gain margin, I have a 8 dB gain margin. Okay, blah blah blah, like that. Okay, okay, it's measured in dB, right? Okay, now like what I said, this is not the only way to affect the Nyquist plot of the G of S. There's another way as well, is to affect the phase. Okay, see, the phase margin is going this way because you see, if you want the plot to cross this -1, 0 point, to apply again is one way. You see, to go measure this crossover and push this one to reach the -1, 0 point. It's one way to show the encirclement happens. The other way is what? Okay, I can, I do not change the magnitude. Okay, let's say if we do not change the magnitude. Okay, if you do not change the magnitude, then what? Then you're gonna see that you only change the phase. Now, how are you gonna measure that you do not change the magnitude, you only change the phase? You see, this unit circle basically give you a good reference, because you see, you're gonna have another crossover point happens here, and this is between the g of s's Nyquist plot and the unit circle. This unit circle, you see, under this unit circle, this crossing point represents magnitude is what? Always 1. Okay, always 1. So can you imagine if you just change the phase? See, this crossing point has a vector, point to here, and this vector will carry a phase here is going to be the theta, right? Okay, okay, this is its phase. So can you imagine, you do not change the magnitude of the plot, but only change its phase. So you can see that the trajectory on the unit circle will provide a very good reference. Okay, so you have two ways to affect the phase of the plot. Either you see, you apply a positive phase, so that this guy plus a delta that is larger than 1, larger than 0. So this way, because this is measured in negative, so you add a phase, positive phase. That's just like you drag this vector along the unit circle. You're gonna go this way. Okay, see, the phase is gonna be becomes larger. I mean, in a negative way, it's smaller, right? Okay, the phase is gonna rotate is gonna goes this way, but with the same magnitude, all unit, right? Okay, so you're gonna see the vector. It's gonna rotate along the what? The trajectory is gonna be on the unit circle. Only the phase changes. Magnitude does not change. So if you apply a positive delta t larger than 0, then you're gonna see this crossing over point with the unit circle. It's gonna stay away from the -1, 0 point, away and away, right? Okay, don't forget it. The -1, 0 point is also on the unit circle, right? It's also on the unit circle, right? Okay, so I'm gonna erase this, make it clear again. Okay, okay. See, so this is like you have a phase here, theta. Okay, okay, and then you're gonna, if you add a delta t larger than 0 here, then the rotation is gonna happen, like this. Okay, so this point is gonna move to here, and going this way, right? Counterclockwise, rotated and counterclockwise. Okay, and see, so this crossover point is gonna stay away this -1, 0 point away and away and away. So what? So that your system will be stable. You don't need to worry about it. But if you add a delta t that is less than 0, negative phase in, then you actually push the crossover point going this way. Okay, it will move this way. Okay, so that you can see that there is a chance when you add a angle here, so that this crossover is going to be right at the -1, 0 point. Okay, so now you can see that this is going to be the critical, right? Just like the gain crossover case, right? So you reach the -1, 0 point. If you continue to add a negative phase to this Nyquist plot, what happened? Then you're going to see the plot is going to go this way, and the encirclement around the -1, 0 point is going to happen. Okay, so you're going to push the system to be what? Unstable. Okay, and exactly if this is the plot, exactly how much negative phase delta could be allowed to be added to the plot? Yeah, it is this alpha, right? It is this alpha angle, this angle. And this angle is what? Is equal to pi plus theta. don't forget it. Theta is measured as a negative. So pi plus theta actually is the pi minus the double bar theta, right? Okay, so this one is measured as a alpha, this angle, okay? Okay, and this is how much for this plot, for this system, how much you can rotate it negatively, okay? If you add a more angle, negative angle than alpha, okay? If you add a more angle than alpha, then what? System becomes unstable. So it is reasonable to define this alpha to be what? Phase margin. Okay? So the phase margin is gonna be showing up in this 3-step again. Okay? So how to do that? How to calculate this? Okay, let's look at this. Okay? And once again, here we are concerned about, you see, here the crossing over point we are concerned about is this one. And correspondingly, you're gonna see there is a crossover frequency, and this time is what? It's omega PM, the phase margin crossover frequency, right? You're gonna see that this phase margin crossover frequency, it's gonna be very important in characterizing the system performance. Okay, later on we're going to talk about that. Okay, this is going to be a very important parameter to characterize the system's performance. Okay, and don't forget, this is you can find this omega pn from the open loop system's Nyquist plot. Okay, so this is a crossover frequency. Okay, so now how are we going to find out that? Yeah, you see, this is the way to find out that. This first step, you need to set the double bar of g of j omega, okay, double bar of g of j omega equal to 1. Okay, its magnitude actually is equal to the real part square plus the imaginary part square. You don't need to tell me how to get this, right? This the magnitude of the frequency response of an open loop system is going to be calculated this one. So you set up equal to 1. Why is set up equal to 1? Because this point is on the unit circle, right? So the magnitude is 1. This magnitude is 1. So that's why you set up this equation equal to 1. And then you can solve this omega pm. Okay? Then you can solve this omega pm. Okay? Okay? And this crossover frequency. You find the crossover frequency. Okay? Corresponding to this crossover point. Okay? Okay. Now, once you find out that, then what? Then you need to calculate its phase right at this frequency. Right at this frequency. This one. You need to calculate this guy. Okay? How to calculate this guy? Yeah. In the second step, this phase is right equal to the arctangent imaginary of the g of j omega over the real part. Well, again, you don't need me to tell you why it's like that, right? So this is very easy to figure out. Okay, it's a phase. It's gonna be because right now you already know the omega p, pm. So that is why this value can be calculated. So its angle represented can be calculated too. Okay, so this is the well, it just need to be careful is that this I'm sorry, this should be the theta. Okay, this should be the theta because the theta is going to be always valued between the minus 360 degree and the 0 degree. We always use negative. Okay, we always use negative value to measure. Okay, okay. Now, third step, if you how to calculate the phase margin based on this calculation? Yeah, you see, once you find out the theta, the phase at the crossover frequency, then your phase margin phi m is gonna be equal to 180 degree plus theta. Like what I said, because the theta is what? It's always measured in the negative value, right? So that is why the phi m could be positive. It's always positive. right? Okay, okay. So so you're gonna see if the phi m is negative based on this calculation. If the phi phase margin is negative, then what? Then the system is not stable. Okay, you calculate this theta. You could have a plot, that is gonna be the case here. Okay, see, if you have a plot here, crossover happens, and then you're gonna have a vector here, and this angle is what? Is minus 180 degree plus this angle, right? Plus, let's say this is a beta. Okay, so you add a 180 degree, then what? Cancel each other. You're gonna left this beta. You see, this beta is negative measured, right? Negative measured, so you're gonna have a negative phase margin. That is unstable case. Okay, so for a stable system, the phase margin is always positive. Okay, which means that this point, this crossover is always stay below the -10 point. So this 3-step is the way to calculate the phase margin. Okay, to calculate step 1, step 2, and step 3. Okay, so you can easily calculate the phase margin, and you also understand that the phase margin means that how much you can rotate the plot clockwise. Okay, how much you can rotate the plot clockwise. Okay, how much you can rotate the plot clockwise. Okay, okay. So you need to be careful to look at this figure. Okay, okay. So that's about gain margin and phase margin. Okay. Any question about this? Any question about this? Okay. Yeah. Any question about this? Hello? No more question? Great. Okay. No more question. We're gonna move to the next. Okay. 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 So this is on the Nyquist plot. Okay. Yeah. Nyquist plot is easy to see for definition. Okay, but it's not easy to play for design. Okay, so later on when we talk about the design, you're gonna find out that actually the Nyquist plot is not easy to play for the the design. But the Nyquist plot is pretty straightforward. It's a pretty straightforward, right? Because it has a geometric shape there. So for you, you're gonna have a better view of what is the gain margin, what is the phase margin, okay? And you have a good geometric, mathematical, interpretation, okay? But for design, it is still the body plot that is easier to play with, okay? It is always a body plot that is easier to play with, okay? So just remember. So that is why we need to identify where this crossover, this 2 crossover point is gonna be on the body plot, okay? On the body plot. Yeah, you see here, this figure shows a straightforward correspondence, okay? See, for the gain margin crossover point, I marked it with the red point, okay? And it's corresponding to the body plot point here. Why is it like that? You see, like what I said, this crossover, you have a phase that is what? Minus 180 degree, right? Okay? You have the phase is minus 180 degree. So you can see, okay, so if you want to identify this point on the body plot, you need to identify first where is the minus 180 degrees line, okay, right? Where is the minus 180 degrees line? Okay, so you identify that, then you're gonna see the plot. Well, you're gonna mark the phase plot cross the phase across the minus 180 degree line. And that's your crossover point for the gain margin. Here, mark the, both of them marked as red, okay? Okay, see, this is a point, this is 2 points corresponds to each other, okay? And how to identify that? Let me repeat that. You use the Bode plot's phase plot and identify its crossover with the minus 180 degree line. Okay, this line, crossover, right? Okay, so this crossover, once you find this crossover, then you're gonna see, in this case, this crossover frequency is your omega gain margin. Well, the figure, book is like the omega C, okay? It's always like the omega C. It's okay. It's just a different symbol, okay? So this one, it's gonna be your gain margin crossover frequency, okay? Gain margin crossover frequency. Okay, now how am I gonna identify the gain margin? Yeah, you see, you find this frequency. Well, don't forget it. You also have the magnitude plot, right? So you need to draw a vertical line to see how much is this value. Okay, okay. This value is what? It's your value here. Okay, this value is your value here. Okay, okay. You see, this is the 0 dB line, and you can see this magnitude is below 0 dB line. Well, that means that corresponds to the magnitude itself is less than 1, which is this crossover case. If you have a crossover like this happens, the magnitude of the crossover point is what? Is larger than 1. So what? Then you're going to see the plot is here. Okay? See, then you're going to see the crossover, point. Then you're going to see the magnitude plot is here because it's larger than 1, above the 0 dB. Now, you can see in this case, this is the unstable case, right? Okay? See, this case will give you a negative gain margin, okay? Negative gain margin, okay? So you can calculate it because in this case, your gain margin value, see, the gain margin is calculated here, right? See? Gain margin is calculated here. Negative 20 log real G of J omega. If this real crossing is larger than 1, the double bar is larger than 1, okay? And then what? Then you're going to have a negative gain margin, negative dB, okay? So this is the unstable case, right? Okay, so you can easily identify that from the Bode plot, okay? From the Bode plot. So very easy to identify. You just need to find this crossover point with the minus 180 degree, and then see corresponding magnitude if it is below the 0 dB or above the 0 dB, okay? If it is below the 0 dB, you have positive gain margin. If it is above the 0 dB, you have a negative gain margin. The system is not stable. Okay? The system is not stable. Okay, so what about the other crossover point? Okay? This is the crossover point with a unit circle. Well, what is a unit circle? Magnitude is equal to 1. Oh, so now you know that in dB, that is exactly the 0 dB level, right? So that is exactly this 0 dB level. So you can see that the magnitude plot cross the 0 dB, this point, it is the right phase margin crossover. Okay, so at this frequency, you're going to identify another crossover frequency, which is exactly the omega phase margin. Okay, omega phase margin, right? So now in this case, then you're gonna see if this phase, where is this phase? Well, you see you need to see if this phase magnitude is stay above the minus 180 degree or not. If it is stay above the minus 180 degree, is this case. If it is stay below the minus 100 degree, then it's what? Is this case, right? Okay, is this case. Because it's larger than, the phase is larger than minus 180 degree. I mean, it's below the minus 180 degree, right? So definitely the phase plot is going to be here, okay? So if the phase plot stay above the minus 180 degree, then you're going to have a positive phase margin, which is this alpha, okay? Which is this alpha, okay? And this is going to be your alpha, okay? Right? See, this basically shows that how much is going to be the margin that you can do to bring the phase plot down to the minus 180 degree level, okay? But if the phase plot is below the minus 180 degree level, which is corresponding to this point here, then what? Then the system is not stable, okay? You see, in this case, you can't bring the phase down. You don't have the margin to bring it down. Instead, you actually have a negative phase margin. Negative phase margin, okay? Because this one is below the minus 180 degree level. So if you add a 180 degree in, and you calculate that this value is actually negative, okay? This value is your negative phase margin. So the system is not stable, okay? So you can, through this correspondence, through this, let me repeat that again, okay? And through this correspondence process, you can identify two crossover points, okay? One is here. This is the phase margin crossover point, which is you need to look at a 0 dB line. And the other one, the gain margin crossover point, you need to look at a minus 180 degree line, okay? Minus 180 degree line, okay? To identify these two crossover points. And they are corresponding to the two crossover points on the Nyquist plot like that, okay? So this figure, this two figure, you need to identify and remember it, okay? Otherwise, you're gonna confuse about how to read the Bode plot, because you know what? In future, when we talk about the control design, we'll just skip the Nyquist plot part. Okay, we'll skip this part. We're not gonna draw the Nyquist plot. Okay, instead we're gonna draw the Bode plot straightforward, and then play everything on the Bode plot. So you need to get familiar with the Bode plot's interpretation of the stability margins. Okay? 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 Okay, let's see an example. Let's see example here. Okay? The example here, yeah, it is, you have an open loop system. It's like a 50 over S and S plus 3 and S plus 6. Okay? Now, for this system, yeah, you see, this one carries a pole on the origin, right? It has an integrator. So it has a pole. Open loop system has a pole at the origin. So remember, we said that in this case, the Nyquist contour has to be modified, right? To modify to exclude the pole S to the left top plane, right? So your Nyquist contour is going to be modified here. Okay? Okay? It's going to be modified to exclude this poles to the, treated like the left top plane. Okay? Right? Treated as a stable one. Okay? So for this system, when you count the P, apparently P is equal to 0. The open loop system is stable. It's treated as stable. Okay? So then we need to draw the Nyquist plot. Yeah, you see, right, in this case, because you have a pole at the origin case, because of this small indent, this small indent happens in the denominator. So that's why you're going to see the magnitude of this one. It's going to go in very large. Okay, actually it's infinity, right? So you're going to see the plot is going to close to the infinity, very large, place. Okay, it's like that. Okay, but anyway, it will close at that place like that, so that the Nyquist plot is going to be carry a shape like this. Okay, so where is the -1, point? It's here. So you can see that apparently the n is equal to 0. There's no encirclement around the -1, point, right? No encirclement around that. Okay, so you can predict that this is a closed loop system. You don't even solve it, and then you can say, oh yeah, the closed loop system is stable. Okay, the closed loop system is stable. Okay, so you get it? You get a point, right? Okay, the closed loop system is stable. Okay, and so yeah, the closed loop system. Well, actually, you can calculate. Well, in this case, you can can calculate the closed loop system's poles, right? Okay, but what I'm saying is that you actually do not need to calculate this pole. Then you're going to know that all of this pole is going to be the left-out plane. Okay, you may not know exactly where the pole is, but you know it's definitely in the left-out plane because the closed loop system is stable. And if you calculate that, yeah, it is this. It's one real pole and a pair of complex conjugate pole. And the real pole carries a negative real part, right? The complex poles also carry a negative real part, right? So apparently all of the three poles, closed loop poles, it's in the left-out plane. So the closed loop system is stable. Okay? Okay? But what I'm talking about here is the you do not need to do that. Okay? You do not need to calculate what is going to be the closed loop system, right? But if you want to verify, you can still do it. Actually, I want to go use this example to show you what is going to be the different application of the Rose-Hurwitz stability criterion and the Nyquist stability criterion, so that you can appreciate Nyquist stability criterion. Okay? You see, if you want to use Rose-Hurwitz criterion to verify if the closed loop system is stable or not, you know what? You do need to derive the closed loop transfer function. Okay? You need to calculate this closed loop transfer function. Okay? Okay? You need to calculate this closed loop transfer function, which is here. Okay? Right? You see? You calculate. Okay. And then after you calculate closed loop transfer function, find out its denominator, because this denominator's equation, polynomial equation, is going to determine all of the closed loop poles, right? Okay, see, you find out the denominator equation, which is here. Okay, then what? Then you need to solve a third order, system, polynomial equation, right? Okay, yeah, it is solvable. Okay, but it's more complicated, right? Okay, but if you do not want to solve this polynomial, then what? Then you can apply Rose-Hurwitz criterion. Remember, Rose-Hurwitz criterion to this specific closed loop transfer functions denominator polynomial equation. Okay, okay, be careful. Okay, Rose-Hurwitz criterion actually can be applied to evaluate any polynomial equation. But when we come to the control system, if we want to use Rose-Hurwitz criterion to identify the closed loop system stability, we have to figure out the closed loop transfer function's denominator polynomial equation. You got my point? Okay? See, this is exactly what I'm doing here. Okay? First, get its closed loop transfer function, then get its denominator polynomial equation, then apply the Rose-Hurwitz criterion to that specific, polynomial equation. Okay? Okay? Not other, polynomial equation. Okay? If you apply Rose-Hurwitz, to other polynomial equation, you got the wrong information about the closed loop system stability, right? So you have to, in other words, you have to have the expression of the closed loop transfer function's denominator polynomial equation in order to apply the Rose-Hurwitz criterion. You got my point? Okay? Okay? See, in other words, you need to know what is going to be the closed loop system information in order to apply the Rose-Hurwitz criterion. Okay? Otherwise what? Otherwise, you won't be able to tell the closed loop stability. But for the Nyquist stability criterion, I do not need this transfer function. I only need this one. Open loop system. Yeah, I need to know it's a Nyquist plot, right? Okay? I need to know it's a Nyquist plot. Okay? Okay? So once I know this information, then I can tell you if the closed loop system is stable or not. This is nice, right? This is nice. We only need a closed open loop system, information to derive the closed loop system stability information, right? Okay, so you can, after the class, you can apply practice, okay? You can apply the Rose-Hurwitz criterion to this polynomial equation to find out if it is true that three roots of this polynomial equation are all in the left-hand plane, okay? You know how to use Rose-Hurwitz criterion, right? So this is, I just, like once again, I just want to use this example to show you when you can use the Rose-Hurwitz criterion to tell the closed loop stability, and based on what information you can actually use the Nyquist stability criterion. Okay, the information they need is different. One only needs open loop information. The other one, you need a closed loop information, closed loop systems information. Okay, so they are different. Okay, but they can do verification. You can check each other because their conclusion is going to be the same. Okay, you use a Nyquist stability criterion to predict that a closed loop system is stable. Then you apply the Rose-Hurwitz criterion to this closed loop transfer function denominator polynomial equation. You're going to get the same conclusion. Okay, the conclusion must be same, right? So you can use this two criterion to verify each other. Okay, to verify each other, right? Okay, so make sure you do that after the class. Okay. Okay, now what about the Bode plot? Yeah, you see, I'm gonna draw the Bode plot of this guy. Okay, and this is actually it's looks like once you understand the correspondence between the Bode plot and the Nyquist plot, and actually Bode plot can be much easier. Right? You see, if you draw the Bode plot, this is the magnitude of Bode plot for this guy. This is the phase plot of this guy. So yeah, like what I said, first let us do some prediction, because you see, I have a third order, denominator for the open loop system. So you can predict that if you draw the phase plot of this guy, the phase is gonna be between 0 and minus 270 degree, right? Okay, we said that the phase range actually it's equal to the minus 90 degree multiply the order of the denominator. Okay, if you have first order between 0 and minus 90 degree, second order 0 and minus 180 degree, third order 0 between the minus 270 degree, right? Okay, but you see this system, because you have an integrator, so this integrator is going to be at a negative 90 degree anyway. So you can see that the remaining two terms is going to maximum offer the minus 180 degree. Okay, so this is going to be on top of the minus 90 degree. So that is why it is not a surprise to see its phase plot starting from what? Minus 90 degree. Okay, instead of starting from 0. It won't reach the 0, right? Because you have a baseline. The baseline integrator gives you always a negative 90 degree, for sure. So your phase is going to start from the minus 90 degree, okay? It will not start from the 0. But still, we say that the range is between 0 and the minus 270 degree, right? 0 and the minus 270 degree. Okay, so like what I said, in order to find the gain margin, crossover point, I need to find the minus 180 degrees line, which is here, the red point, right? Okay, and then this is its magnitude. The magnitude, yeah, once I find this crossover point, you see this is going to be the crossover frequency. Actually here, it shows that the gain margin, the crossover is right at the 4.24 rads per second. By the way, this plot is produced by the MATLAB, right? By the MATLAB. So if you use the margin command, if you use the command margin, and it will give you both the gain margin, phase margin, and the crossover frequency. Okay? Okay, so this frequency is going to be the 4.24 rads per second. Okay, then you're going to calculate this. How much is this? Well, this is equal to the gain margin is calculated as the 10.2 dB, which means that this magnitude here is negative 10.2 dB. Okay, it's right equal to the negative 10.2 dB. Okay, so the gain margin is calculated as the 10.2 dB. Okay, which means that you can increase the gain K by 10.2 dB. Okay, you can multiply a K here, and this K can be increased by 10.2 dB. No problem. Will not jeopardize the stability. But if it go higher than that, you jeopardize the closed-loop system stability. The closed-loop system will not be stable. Okay? Okay. What about the phase margin? Yeah. Phase margin, like what I said, you need to identify the 0 dB level, right? This is the 0 dB. Okay? So once you have the 0 dB, and then you're going to see the crossover point. This is the phase margin crossover point. So then you need to find out its phase. Okay, now you can see on the phase plot corresponding to this one, this crossover frequency actually is equal to 2.13 rads per second. Okay, so you can calculate its phase right now here. Okay, the phase margin is actually the 35 degree, which means that this is going to be the 35 degree. Okay. And what about this phase? Yeah, the phase of this crossover frequency, the system will exhibit a phase that is minus 100 degree plus 35 degree, which is right equal to the 145 degree. See, this is going to be the minus 145 degree phase. That will yield a positive 35 degree because the magnitude phase plot is above the minus 180 degree level, right? So you're going to have a positive phase margin. Okay, so you can see that from the body plot, you can see it very clearly. This system has both positive gain margin and a positive phase margin. So the closed-loop system definitely is stable. Okay, so the closed-loop system is definitely stable. Okay, okay. So you can read the stability from the open-loop system's body plot. Okay, you see, you only need to draw its body plot, then you can read the stability. Okay, you can read the stability. Okay, so this is what we mean here. Okay, now I'm going to show you that why if you increase the K, then the system could become unstable. Okay, let's see if we increase the K, what happened to the body plot? Okay, now, so you can see, let's say, okay, so let's say if you add a K here, okay, and then increase the K from 1, so K is larger than 1, right? Okay, so now you increase the K, okay, increase the K. How this K is going to affect the body plot? Okay, so you know that because you increase the K. So basically, this is just like you are raising the what? You are raising the magnitude plot. Will the phase plot to be changed? No, the phase plot stays the same. Okay. Okay, so you keep increase the magnitude plot. You see, the phase plot does not change. So that is why the phase, gain margin crossover point, this 4.24 will not be changing. Okay, because the phase plot stays the same. The magnitude plot is going to be raised up. Okay, so now you can see that if this crossover frequency does not change, then you raise the plot like that, magnitude like that, you can see what happens to this gain margin. You see, you raise the plot, you could raise the plot above the 0 dB. So your gain margin becomes negative. Okay, your gain margin becomes negative. So the system becomes unstable. Becomes unstable, right? Okay, this can be also seen from the phase margin. Because you raise the plot, you actually push this crossover point to the right. You see, the new crossover point is here. This is 0 dB, right? You see, you raise the plot, the crossover with the 0 dB line, this crossover point is going to be pushed to the right. But the phase plot does not change, right? So if you push this point to the right, you calculate, you see, okay, now your phase margin now becomes negative. Okay, the phase margin, well, yeah, if the K is decreased, then the system becomes more stable, right? Okay, you can analyze that, accordingly. Okay, you bring the magnitude down, right? You bring the magnitude down, right? Okay, so it's easy to see that, it's easy to, you see, in this case, you're going to have here, okay, you bring the magnitude down. So the system becomes more stable because you increase the margin, right? You see, if you bring the magnitude down, the phase plot still does not change. The gain margin is going to increase from this much to this much, right? Okay, and the crossover with the 0 dB is going to be pushed to the left. Push it to the left, you see the phase margin is going to be increased from here to here. Okay, so that's why if you bring the K down, the system becomes more stable. It's well, I don't care about that. I don't care about the stability. I only care about if I change the K, how the stability is going to be damaged, right? Okay. Okay. Well, yeah. You need to recalculate. If you change the K, definitely you need to recalculate the gain margin and the phase margin. All right. Okay. Right. Okay. Apparently, because you see, from the body plot, it is very clear. If you change the K, it will change both the gain and the phase margin. Okay. Change both the K and the phase margin. So you need to recalculate the phase margin and the gain margin. Okay, now here I'm telling you one way to calculate the phase margin and the gain margin. Okay, numerically. Okay, see this way here is that graphically. Okay, see you have the expression of the open loop system. You can get the body plot. Yeah, then you can identify the gain margin crossover point, the phase margin crossover point on the plot, right? So this is a graphic way. But if you have the expression of the open loop system, you actually have a numerical way to calculate it. Okay, they are consistent. They are consistent. Okay, so I'm going to show you how I'm going to do. Okay, yeah, this before k is raised up to the 10.2 dB, the system will be still stable. Okay, because you see, when you raise the k by 10.2 dB, because here is too small, I need to exaggerate that. And that is the right value such that this crossover is going to happen at this point. You see what I mean? Okay. If the k stayed below the 10.2 dB, okay, you won't see the crossover at the -0 point. So the system will still stable. Okay. Only when k is increased more than 10.2 dB, then this magnitude is going to above the 0 dB. Okay. Okay. Crossover is going to be above the 0 dB. Then, you know, the system will not be stable, right? So that is what we call the margin, right? Call the margin. You see, again, let me go back here. This is the how much. This is how much you can raise the gain. Okay. How much you can raise the gain, right? Because you see, you keep raise the magnitude, and this the crossover, the 0 dB crossover is keep it keep it to the right. Yeah, when you raise the 10.2 dB, this point is right at this point. Okay, right at this point. Okay, and then if you continue to raise the k, and then the system will not be stable. Okay, okay. So now, yeah, here. I'm showing you the numerical way to calculate the gain and the phase margin. Okay, so this way, if you do the numerical calculation, you don't need a plot. Okay, you don't need a plot. Okay, I actually do not need to a blank sheet. It's here. The procedure is here. Okay, the procedure is here. Okay, yeah. Okay, so now let's do it one by one. Okay, first, yeah, I have the expression of the frequency response for this transfer function, right, which is here. And then you need to do rationalization of the denominator. So that's why you got this expression. Okay, so do not tell me again. Okay, do not tell me you don't know how to do it. Okay, because this has been done, you know, in the control one a lot of times, right? So rationalize the denominator, and yeah, then you're gonna see that you actually have the real and the imaginary part, right? Okay, you have both the real and imaginary part. Okay, so then you're gonna set up the imaginary part, calculate the gain margin according to that procedure. So you're gonna set up the imaginary part to be 0. Okay, so that is this part to be 0. Forget about the denominator, right? So only the numerator is 0 is good enough. So that is why you can easily solve the gain margin crossover frequency. It's going to be equal to square root of 18, which is a 4.4 rads per second. Is that right? You see, 4.4 rads per second. This value. Okay, you see, you can easily calculate the gain margin crossover frequency. Okay, then you calculate what is going to be the real part of your frequency response at this crossover frequency. Okay, so you substitute this frequency into the real part, which is here. Okay, and see, 54.24 minus 9 multiplied 4.24 is here, right? Okay, and then denominator is omega squared, and let me erase that. Okay, see, your real part is here. Okay, and that is exactly equal to here. You substitute the omega crossover frequency for the gain margin, which is 4.24 into this expression. Yeah, then you calculate that. Oh yeah, you see, at the crossover point, the magnitude is actually equal to minus 0.37. Okay, minus 0.37. That's the real part. Okay. Okay. Then third step is we use the gain margin formula to calculate the gain margin. So it's going to be equal to the minus 20 log double bar real, yeah, double bar, right? You need to take the absolute value, okay? Not the real value, okay? The real value is negative. You take the log, it doesn't make any sense, right? So you take the double bar, that's going to be the minus 20 log 0.31, which is exactly, you see, equal to 10.2 dB. Correct. Consistent with the value here, you see? Okay. Okay. Now, what about the phase margin? Okay, the phase margin. Okay, so you calculate the phase margin. Okay, so phase margin is a little bit more complicated in this case. Okay, because you have a higher order system. Because you see, what happens is because you need to make the magnitude of frequency response first equal to 1. Okay, first equal to 1, which is here. Okay, so you calculate its magnitude. The magnitude is going to be double bar of this guy and double bar omega multiplied square root, right? Okay, make this one equal to 1, and then that will give you an equation like that. Yeah, you see, this one it's a very weird, you know, polynomial equation, right? Yeah, you can use it. You can definitely use MATLAB to solve that. Okay, but if you do not use MATLAB, you know what? You actually can use Rose-Lewis criterion to solve it. Okay, to find this omega, the phase margin crossover frequency. Okay, you know, we talk about the how to apply the Rose-Lewis criterion to solve a polynomial equation with the singular case. Remember the singular case, right? I'm not going to talk about that here. You just need to recall, go back to check the Rose-Lewis criterion. So I'm going to suggesting you that to try Rose-Lewis criterion to this polynomial equation to find out what is the phase margin crossover frequency. Okay, do not use MATLAB. If you use MATLAB, definitely you can solve it. Okay, that's no problem. But to help you better understand this, you know, try to use the Rose-Lewis criterion, because you're going to see this is the singular case. Remember, for the Rose-Lewis criterion, we talk about the two singular case, right? We also talk about how to deal with those two singular case. This is one of the singular case there. So you can apply the Rose-Lewis criterion to find this value without using the MATLAB. Okay. Okay. So I would highly suggest that you practice that. Okay. You go back to practice. Okay. After class. Okay. You know, it's a good practicing, and it's a help you better understand the Rose-Lewis criteria. Okay. But anyway, so you can solve the phase crossover margin is equal to 2.13 rads per second. Yeah, which is exactly what happens here. Which is exactly, you know, what happens here. You see, phase margin crossover point is this crossover point. Okay, 2.313 rads per second. Okay, so you find this crossover frequency, yeah. Then you use this formula to calculate the phase of this guy, at this frequency. So yeah, according to this formula, you see, okay, because you have both negative, both the imaginary part and the real part, right? So that is why you see you can substitute the imaginary and the real part here. You see the denominator doesn't matter here anymore. Denominator doesn't matter here anymore, right? So only the numerator matters, because both of them share the same denominator. So that is why if you calculate this ratio, that is right equal to this. Okay, the 118 minus omega square PM over the 9 over omega PM. Okay, you see, it's just equal to the imaginary part over this one. Because why you got a positive sign here? Because both parts are negative, right? Both parts are negative, so you got a negative sign. Okay, So you substitute this value here, and then just do a straightforward calculation. Okay, calculate arctangent value. Okay, just do a straightforward calculation. You find out this phase actually is equal to minus 145 degrees, which is right here. Okay, which is right here. Okay, which is right here. Okay, so you see, like what I said, for the phase margin, I first calculate this crossover point based on what? Based on the magnitude equal to 1, which represents the 0 dB, right? The 0 dB. That represents the magnitude of the frequency response equal to 1. Okay, unit circle. You just, in your brain, you just imagine this is the Nyquist plots unit circle, right? Okay, then corresponding to this crossover point, find its phase here. That is the minus 145 degree, which is calculated here. Okay, calculated here. Okay, then once you have the phase, yeah, the phase margin can be easily calculated by 180 degree plus this theta, which is 35 degree. Same here. Okay, see, this is the numerical way. Okay, you don't need the body plot. You can calculate its phase. Okay, you don't need a body plot. You can calculate its phase. Okay, and the gain margin and the phase margin. Okay, you can calculate their gain margin and the phase margin. Okay, okay. Any question about this calculation and the body plot? Yeah. Okay. Very clear, right? Very clear, right? Okay. Okay. Good. Okay. I have a couple of more minutes, and I just want to say something. And well, yeah. Oh, seems like I run out of slides. Okay. Yeah. I think that's it for today. Time is already here. So yeah, I will, I will take your questions, for a couple of more minutes. Okay. Yeah. Go ahead. If you have any question, you can ask now. Okay. So the lecture is stopped.